think I can probably start, and people still joining. So hi, everyone. Thanks for being here today. It's my absolute pleasure to introduce Kristen Grauman as our keynote speaker today. Kristen is a professor in the Department of Computer Science at the University of Texas at Austin and a research director in Facebook AR Research. Her research in computer vision and machine learning focuses on video, visual recognition, and action for perception or embodied AI. Before joining UT Austin in 2007, Kristen received her PhD at MIT. And she's been an IEEE Fellow, AAAI Fellow, Sloan Fellow, Microsoft Research Fellow, and the list continues to infinity. And she and her collaborators have several Best Paper Awards in computer vision, including a Test of Time Award. And Kristen is involved in multiple editorial boards and program committees of influential computer vision and machine learning journals and conferences such as CVPR, NeurIPS, and so on. So today, Kristen will be presenting Look and Listen, audiovisual learning in video, which we look forward to listening to very much. And the way that we're going to do it, as Frederick said, feel free to post any questions in the chat or in Slack as we go. And we will have a Q&A session at the end, in which I'll read some of those questions, and you can also unmute yourselves and ask questions to Kristen directly. So with that said, Kristen, it's all yours. Thank you.
Okay, great. Thank you, Magdalena, and thank you, Frederick. Thanks to all the organizers for having me here. I'm very excited to have this chance to talk with you all. As you just heard, I'm a researcher coming from computer vision, but a lot of my work in the group has started to focus on audio-visual learning in video and for embodied perception. And so this talk is going to focus on some of the latest results that we have there. And I'll be very eager to have your questions and comments, especially given the kind of interdisciplinary nature of this work. So I am motivated to consider, how to teach a computer vision system. This is a fundamental issue much research is attending to. And a classic way to teach one is to do so with labels and images, or maybe labels and videos, such as the famous ImageNet challenge, which is labeled in the way you see here, and many, many other influential benchmarks. Of course, for a long time, this has been a process of learning in which the inputs are silent. And so it's kind of a visual moment in time or a snapshot taken out of the context of the activity. When in fact, we know that everyday scenarios have so much to offer, both in terms of what we see and what we hear. And so what are those things? If we start to think about computer vision with audio as a first-class citizen to help us learn, we could learn things about the materials. So objects look a certain way because they have a material. They also sound a certain way when those materials interact. We can learn about an object identity. Some objects have signature sounds that they emit. We can learn about dynamic sources, events that happen in the world that we want to go trace and find. Spatial cues, as we'll get into in detail in this talk, sounds that move around and indicate something about where things are or where we are. Emotion of people, like we just saw in that example. And finally, scene noise, so ambient sounds that tell us something about where we are, not just by what we see, but also what we hear. So that's just a smattering of, a portion of the things that we'd hope to be able to capitalize on, bringing audio and vision together. And in this talk, I've split the work I want to share into two parts. The first one is thinking of audio as giving us more semantics. Semantics, we usually mean things like objects and activities alongside the video. And then the last part of the talk, I'll turn instead to spatial elements of the sound and how that works together with the spatial information in pixels. So let's start with the semantic signals. And here I want to begin with the task of visually guided audio source separation. So in audio source separation, we want to take the input audio and split it into the different sources so we could hear one at a time. When it's visually guided, we also get video. We get frames that show us what was happening. And this is a really powerful addition because of the fact that the motions of objects and of people and maybe even their lips moving are going to give us a signal that helps a separation beyond the audio alone. And in fact, there's been both classic methods in this vein, as well as a recent resurgence of methods trying to account for the visual stream when performing source separation. And in particular, one of the recent successful methods has taken a learning-based approach that can be nicknamed mix and separate. So these are models that turn to deep learning and video data to learn how to do the separation task. And the mix and separate is very nice because it says you could take 2 training videos without knowing much more about what they are and mix their audio. And now you have both visual streams for either one, and you also have mixed audio that you could learn to separate. So in other words, if you took their original waveforms that were blue and red, now you can train a model to listen to the mixed sound in black and watch one of the videos and know that it's supposed to disentangle and take out, say, just the waveform in red for the bottom example, and vice versa for the top. Now, this has shown a number of good results, some of them referenced here at the bottom, but where it falls short is that it really wants to have single source audio for training, meaning single source videos. And by that, I mean, ideally, this should have one object making sounds in a video and another object making sounds in the other. As soon as you have multiple sounds in the video, there's no signal in training about how to disentangle those, right? And furthermore, this is related to the second limitation that this model would ideally like independent sources in each recording, when in fact, the kind of sounds that happen together may tend to happen together a lot. And so then how are you going to learn to disentangle those? So let me tell you then our idea here that we pursued recently. It's got a computer vision analogy that I'll mention briefly here. So the analogy is to what's called co-segmentation. And in image co-segmentation, you have images of the same object, but on different backgrounds, like on the left. And no one tells you anything else about the foreground, but it becomes easier to find because you know that something's recurring in the midst of some other kind of background clutter. So that you could co-segment, meaning segment out the foreground together, better having the 2 views than if you just had one view at a time. So that's a good analogy for the type of approach we're proposing for audiovisual source separation. And we call it co-separation for that reason. And what we'll do is at training time, we'll have pairs of video in which we can have multiple sources. So no longer restricted to single source data. And we'll detect objects visually, automatically. So maybe we detect these different instruments. And we will do the mix of the audio for training. But now what we'll say is that we want to be able to separate sounds for all detected objects that are sound emitting objects. And importantly, do so in a way such that there's consistency of the sounds associated to the same visual patterns, in this case, the same visual object. So what does this mean? It's saying, just like my past slide, it says we don't know yet what a guitar sounds like, but across all these training samples, as we keep seeing them, we'll do the separation even at the training instance level so that the things associated with guitars are consistently identifiable. And that term just means they're not exactly the same, but it means we could have a model that would group them together, classify them together, to realize that this is the sound that's common for guitar. So this is the key insight for co-separation. And I'll tell you a bit more then about the model and how exactly this works. So during training, we have 2 videos coming in at a time, V1, V2. We will mix their audio. And from there, we have a spectrogram for the input mixed audio. And now our job is to produce masks on the spectrogram that would separate out the sounds for each sound source. So on the top video, let's suppose we detected 2 objects, a guitar, a saxophone, and on the bottom, maybe we just detected 1, a harp. Now we have a network, a neural network that's going to do the separation, and it's trying to compute these masks on the spectrogram, producing the separated sounds. Now, these are going to be learned to respect two different losses. And the first loss is the co-separation loss. And it says that once we do this masking from the full mixed signal, we should get back, once adding back up the component sounds like X1 and X2 for the top video, we should get back the source video input sound. Okay, so we can reconstruct with the ones that we've separated. And secondly, very importantly, we have a loss on the spectrograms here that says they should be consistently identifiable for the detected object. And that's at the sound level. So now, given the separated sounds that we're estimating during training here, they need to be such that for any instance coming from, say, guitar, C4, they should be clusterable with other instances of a guitar. So again, it's not that we have a classifier that knows what guitar sounds are from the onset, it's that we'll discover one essentially through this separation training process, because it's going to require that these be consistently identifiable. So just to visualize what that means, it's saying here are all these spectrograms of things we're separating during the training loop, and we want them and their learned representations to sit in a space where same objects who should make similar sounds cluster together. And actually, the plot I'm showing you is from real data. It's a t-SNE plot down to 2D for the various instances in a data set from audio set that have the instrument labels that you see on the right. And so the more these colors are clustering together, the better it's able to satisfy that consistency loss. So what's really important here is that we can achieve this with multi-source video. And why do we care about that? Well, because that's the kind of video that's just laying around, right? That means we're not going to go capture videos of one instrument at a time. We'll take videos as they come and now be able to still train with them for source separation. So we've tested this on a couple of different data sets, audio set and MIT music data set. The music one is especially nice because you can split it into those videos that have solos, hence single source, and those videos that have duets or more, which is then multi-source. So here are some of the results that I'll briefly overview. So on the top, audio MIT music, on the bottom, audio set. And these are a variety of different metrics we're looking at and comparing our method, co-separation, with some classic NMF-based separation approach, some audiovisual mix and separate, and some earlier recent work from MIT on the sound of pixels. You can see that quantitatively, this is a good model. On the single source training, things are better. And most importantly, when we allow training with multi-source, we still persist with our advantage. And in fact, in some cases, it's more stable compared to these other models, which, as I said in the beginning, are just not built to handle multi-source training data. All right, so what does it sound like and what does it look like? Here, I'll just show a couple samples. I'll play the original video, and then I'll play what our model would hear for one source and then the other. So here's the original. Okay, and then we separate first the violin. Okay, so that gives you some sense. Now, just for comparison, I mentioned methods that train with multi-source data, but aren't supposed to, meaning they're not built for it, would definitely have a problem. And so you can hear that that method is just not able to disentangle because it's expecting a single source in every training instance. Another example, this one where we're going beyond musical instruments. Here's the original source. And separate the dog or the violin. Okay, so not a perfect separation, but I hope you could tell kind of the focus on one source versus the other that we could pick out automatically. And again, this method in general has learned kind of what to associate, what sounds to be listening for, depending on the object that it sees. There are definitely failure cases and even more egregious ones. Here's one that just cannot be separated well by our model. So you can see it would find objects, but the separation was poor. Part of that was a lack of a person model in this particular data set and our approach there. But generally, the more sounds you have, of course, the more difficult it does get. Now, another final thing I wanted to show here is what it hints at for its understanding of how things look and how they sound. So if you remember, underneath, we're discovering the sound models, basically what sounds go with different objects. And so we can kind of back project and look, okay, if we look at so-called object proposals, which are windows where there might be an object in a given frame of video, we want to know which of those are associated with the highest audio confidence for a given one of those audio clusters. And so each of these rows is one such set of proposals. And it's kind of fun because it means, it's starting to pick up on how these consistent looking things are associated with consistent sounds, from accordions plus an inconvenient striped shirt on the right hand side to the harps or to the guitars and their different parts. All right, so I've shown so far this separation. We focused a little bit on instruments as a means of illustration. I want to talk next about continuing work we've been doing on separation problems before human speech. And this, of course, is the well-known cocktail party problem. We, as human listeners, have no problem being in a busy environment, hearing other people talking around us, but then focusing on one person that we care to hear the most. And the question is, how can we do this well with our algorithms? And I'm going to tell you about our latest attempt here. And there'll be some carryover from what I showed you in the spirit of, when we see something and understand what it looks like, we can better separate it. But now we're going to focus specifically on faces and speech, and we're going to also care a lot about the dynamics, meaning how the person moves in this case, and how their lips move to do this task. So first, let me give you an intuition for the specifics of our approach with a little quiz. Here I show you 5 faces, and I'm going to play a voice, and your job is to guess, which face did it come from.
Alors bon, moi je suis une novice, pour le coup, j'ai jamais vu ça concrètement, mais c'est 2 mois.
Okay, you might have a guess. You might guess face number 2, and this one perhaps is an easier one. There's one female in this lineup I'm showing. I'll give you one more.
People being cool, and you can see that in daily life.
Okay, this one maybe not positive. You might have a guess though. It is face 4. Now, if you have a guess, what's it based on? Well, it's well known that there's visual properties in faces that hint at their voice qualities. And this has to do with gender, with age, even with body shape, body weight, nationality. So all these things can sometimes be visible in a way that would give us a prior for what the voice is like. And in fact, this has been leveraged to train cross-modal embeddings between face images and voices in a series of interesting work in recent years. And what the goal in that work has been is to do person identification so that you could learn these embeddings that are enriched by ID-specific properties. That's not our goal here, but we can leverage this insight because we realize that the task of audiovisual speech separation is synergistic with the task I just described of learning and embedding, where faces and voices that go together are close. Why is that? Well, on the one hand, if you've done a really good job of separation on some video, then you would have distinct voice tracks for each person, and that would make you able to learn a more clean embedding in this cross-modal space. And on the flip side, if you've learned a good embedding for faces and voices, then this would allow you to be listening for or to disentangle the right audio for the right face when you're doing the separation task. So we see this, that, you know, the one would enhance the other. And anytime you see this, it's a good idea to consider, could we jointly train these objectives of separation, in our case, as well as the cross-modal embedding. So that's what led us to develop an approach we call visual voice. Visual voice because this intuition is, you know, you're looking at someone, you see what they look like, even if there's lots of other voices or sounds going around, you will have a prior for what patterns of the voice, what frequencies, what intonations that you should be listening for to hear them better. So it's like seeing the voice in addition to hearing it. And the whole idea is to jointly learn those two things I just mentioned. And so during training, we will do a mix and separate kind of foundation, but here we'll be paying attention to the lip motion, as well as the appearance of the face for the two speakers. And so we'll be targeting that separated speech for the mixed audio for any training pair. But at the same time, we'll be requiring that we satisfy the push-pull objectives in this cross-modal embedding space. And that means pushing, like we want to have the pulling, we want to have the face that goes with the voice close to it in the cross-modal embedding, and vice versa. The one that doesn't should be far. Okay, so we put these things together, we train a model. I'm not going to say more details about exactly how the architecture of the network is constructed, but basically it's taking account both of these objectives so that we can, in fact, do either of them better. And I wanted to highlight some real world examples before I show you some quantitative results. These are just videos we took to try and check, you know, can we take in the wild data and separate the speech. So I'll show you the original as before, and then we'll focus on one voice at a time.
Well, you became a superstar.
No, I did not.
Yes,
no,
you
I
did.
Not. No,
sure
I did
you
not.
did. From
are
me,
you gonna
I
let
gave
me
you full
speak my
credit.
piece?
If you're talking to me now,
am I gonna
I
speak
gave
my
you
piece?
full credit for that.
Am I going to speak my piece or not?
Go
am
ahead.
I going to speak my piece or not?
Go ahead.
Okay, because you want to interview me. I ain't interviewing you. You want to talk to me. I don't worry about talking.
Floyd,
you want to talk
go ahead.
to me.
I'm waiting on you.
Okay, so all too familiar to many of us. You know, you're watching politicians, you're watching talking heads. So here you go. Visual voice can isolate one at a time.
Well, you became a superstar. Yes, you did. Sure you did. From me, I gave you full credit. If you're talking to me now, I gave you full credit for that. Go ahead. Go ahead.
And the other voice?
No, I did not. No, I did not. No, I did not. Are you gonna let me speak my piece? Am I gonna speak my piece? Am I gonna speak my piece or not? Am I gonna speak my piece or not? Okay, because you want to interview.
Okay. So that was people talking over each other. We also can apply the same idea to speech enhancement, where we have people talking in noisy environments like this one.
Haven't measured it, but it's cut down the noise to a point where we have the right vibe that it's an action kind of place.
Now when we enhance the speech of this face.
Haven't measured it, but it's cut down the noise to a point where we have the right vibe that it's an action kind of place.
And finally, an example you might have seen, and we're all, whether you've seen it or not, we're all familiar, I think, in our Zoom work life.
I would be surprised if they do. Pardon me. My apologies.
What was this going to be for the region?
My apologies.
Okay, so he was speaking. Now let's see if we can enhance that speech among all the other sounds.
I would be surprised if they do. Pardon me. Pardon me. My apologies.
Okay, so you get a sense of, you know, working on some real world samples. Now, of course, very important, we've also run this on all the benchmarks we know about for this task. So there are 5 of them, and the visual voice model is improving state of the art compared to existing audiovisual methods. All right, so far in this talk, I have, you know, motivated why we need to listen as well as look for understanding video. And I focused on problems, especially, you know, source separation, where it's really the semantics that are coming out, like things about how the object looks or how it moves that help us do the separation task. Now, in the remainder of the talk, I'm going to shift to really zooming in on the spatial aspect of audio and how that can complement what's already a spatially rich signal, which is images and video. So when we talk about spatial effects in audio, there's two sides of this coin that we'll be modeling and paying attention to. One is the 3D environment. We know that the sound we receive will be influenced by the geometry of the big surfaces and furniture around us, as well as their materials, as well as where we are with respect to sounds that are in that environment. So those are factors from the 3D environment. And on the flip side, we know that our own embodiment will affect and allow us to sense spatial sound. So in humans, we have these two ears, and receiving waveforms to one and then the other gives us factors like the intraoral time difference or the level difference, or even the shape of our ears that's going to affect and reveal where the sound source is placed in the environment. Same goes, if we have a robot with N microphones who's then able to sense sound in a rich spatial manner. Okay, so we know these are things we'll need to account for. And now secondly, for this set of work I'm about to show, when we got into it, we were interested in being able to have reproducible on-the-fly renderings of sound in complex photorealistic 3D environments. And for this, what we wanted to do is provide a platform for ourselves and for future research that would give acoustically realistic 3D renderings for what's already available in terms of visually realistic 3D environments. So if you haven't seen these before, in existing work, people have scanned homes or multi-room apartments, meaning they're photorealistic because they're real environments where you place down scanners, get the 3D mesh for the space. And now with that and with the panorama, 360 panoramas everywhere captured, you can render an arbitrary photo from an arbitrary viewpoint as if you were a robot or a camera moving through the scene. So that existed. And what we did is to add the pre-computed sounds, or really the room impulse response functions for all positions and all possible source positions in these environments. So we basically, with our work called SoundSpaces, we've introduced a platform where you can render state-of-the-art sound propagation results based on the geometry, the materials of the space, and the positions of the microphones and sources in real time. You can do this for the waveform of your choice. So for example, at any of these possible positions, we could place a source and now render how we would receive it with binaural microphones or ambisonic microphones anywhere else in the space. Good, so now you have the ability to do these egocentric first-person measurements of both the vision and the sound. And I'll show you a sample from SoundSpace just to give you a sense of the quality. So on the left, you'll see the ego view of the picture, the RGB. And on the right, you'll see a top-down map of the full environment, which in work I'll show you later is not known to an agent, but gives you a sense of how you're moving in this space. And then you'll hear a little bit of what SoundSpace is producing. Keep in mind to really hear the spatial elements, you'd have to listen to our source file with headphones receiving the left and right ear waveforms properly. But now you'll hear the level difference. Okay, so hopefully you could hear there's a piano playing, it got louder as you approached it. There's a smoke alarm playing, it gets very loud as you approach it. And again, the spatial would be there if you listen from the original source. And this is, this was a real environment, but this video is created by synthesizing a camera path through it, as well as this now microphone path using our SoundSpaces environment. So now let me talk about some of the things we've built because we have this resource, and it's allowed us to train and test some of these ideas in a very reproducible and large scale way. So the first one I want to share is considering a mapping problem. Suppose you have a short video and you want to use it to infer the layout of a house, or rather a floor plan. Now, if you're using a short video, suppose in my example here, it's the cones or the camera positions over time. Now, if you were doing this with vision alone, you know, you can do it great if you put the camera everywhere. This is what we do. Even those meshes, that's where they come from these environments. But if it's short, it means you're not seeing everything. And so, in fact, if you compute a floor plan map from a small video like the one I'm showing, there's only so much you can see. There's only so much that will get mapped. A lot of it will be invisible to the camera. It's behind the camera. It's behind walls. So our idea was to allow, you know, these small videos or short videos to give us full floor plans by also listening. And why should the sound help for this particular task? Well, it'll do two things. One, just the pure geometry that it brings us will be an addition to understand free space around the camera, even if we don't turn the camera in that direction. So the sounds bouncing off walls behind us, we'll be able to sense that if we learn it properly, so that we know there must be some more free space there. And secondly, there's semantics in sound as well. So if I walk by a wall in which there's a kitchen behind it, even though I can't see it, if I hear kitchen-like sounds, like someone chopping or a dishwasher running, then I can have a guess that there is a kitchen behind here. Maybe I've even learned a scale prior about kitchens, so I have that much better of a guess of the floor plan. So that was our intuition. Can we learn to produce these, what we call audiovisual floor plans, based on short videos? Because audio really lets you see more than what the camera sees alone. And we do this for two forms of map outputs. One, an interior map. This is a binary occupancy map, saying where there's walls and where there's free space. And second, a room map. This is a semantic label map that says not only here are the rooms, but this one we think is a kitchen, this one we think is a bathroom, etc. Now, I'm not saying much about the model for time, but the basic idea was to train this in a supervised way. So we take out floor plans from environments like I just showed you, and then we use their dense maps, like the ones shown on my side, as the training output or the target output. And then we train to go from sequences of frames plus sequences of audio to predict those maps. And we do it in a self-attention driven way, so that over time we can accumulate the evidence and use attention back and forth to best estimate it. Now, when we do it, you get results like this. So first I'll show you a static snapshot of one. This is a 3D environment. On the left, the cyan region is what would be produced by a vision-based mapper, one that uses the camera trajectory shown with these orange cones. So, as expected, by looking out, seeing the depth of the scene, projecting it down, you can map out whatever you see. But the green region on the left, the light green, is all the parts we would map using the audiovisual floor plan idea. And it's much bigger, right? Because we can so-called see behind ourselves now with the sound and flesh out the free space much more widely. And here's the 2D projection just to the right of it for the same environment. And we can see that the correct parts are in green or black for true and positives and negative, and the errors are in red and blue. So the message of that example is for the top, we're getting that pretty full green and black area compared to the best we could get with state-of-the-art vision mapping that also does extrapolation of its own, which is shown in the bottom, this occupancy anticipation. So let me show you a video of this then. It's going to be, again, one of these Matterport videos with SoundSpaces to get the sound. And you'll see the egocentric view of our input video on the left, and you'll see the map evolving on the right as we compute it. Okay, so this was a busy household, things going on, the phone's ringing, someone's knocking on the door, there was someone typing in the office. And as the camera went through, you can see the camera trajectory again with the orange cones on the right. We obtain a certain visual map that's in cyan, and again, the larger, more complete map with green, that's thanks to the audio-visual floor plan. And this is, I think, a neat example because here we are using incidental environmental sounds that are there for free in some sense, along with the video, that are helping us to sense the extent of the space and measurably to map it out better. Now, for there, and certainly we've measured the quality of those quantitatively, but for time, I'm going to move on. Now, what we just were looking at was one way to do some 3D sensing about the environment, and in fact, come back with 2D floor plans saying, here's where we think the major areas are. Now I want to go continuing with the spatial sensing from the sound and the vision, but think about it as capturing the shape of the scene. So not just the shape of the floor plan on the ground, but the shape of the scene around us, which in vision we think of as, say, the depth and the shape of objects that surround us. And here we can take some motivation from Hollywood. This movie Daredevil has a character who cannot see, but is attuned to the echoes in the environment so that he can see by listening. So here you'll see him strike this surface and then listen in or see the results. Okay, so no sight in this case, but able to sense the shape of the scene from the sound. So we'll try to do this in a less glamorous way, but we'll try to do it nonetheless, where here we're going to think about understanding the sounds to understand the shape of the scene. And notice that in this case, we're emitting sound. So far examples I've shown you have been focused on environmental sounds that happen to us. And now we're going to think of, well, we can actually control, we can have the agent emit a sound, or we can emit a sound from the camera and then listen to the echoes that result. So the idea that we have to try and leverage this ability, this potential for learning shape from sound, is to do so with a feature learning approach. And so we call this next approach VisualEchoes, because we're going to try and do feature learning from echolocation. And the goal is to learn visual features from echolocation, meaning we have audio at the time we're learning, so that we can benefit spatially oriented tasks that are visual only. And by visual spatial tasks, I mean things like predicting depth, kind of like I just showed, predicting surface normals, or visual navigation. And what's, I think, interesting for this line of work is that it fits in with what's so far a limited line of work, trying to self-supervise a model, not from repositories of static data, but from interacting with the world itself. So self-supervision, this is the idea that you could learn representations not with human labels, but by looking at the signal and using the signal as some means of supervision directly. And multimodal is a great place to do that in general. But here we're taking this idea, but now thinking of it where we're interacting with the world by emitting sounds to get that self-supervision. So what's the model? How do we actually take echoes to build better visual features? So during training, what we do is collect samples of the RGB, the depth, and the echoes we receive when we face a certain way in the scene. So here, looking top down at that map, maybe I'm facing to the left, and that's what I see, and that's what I hear for echoes. These are spectrograms for the left and right ear on the right. And we can do the same at any viewpoint in any position. So we would amass a set of training data that says, here's what it looks like, here's the actual depth, and here's what the echoes will sound like if you emit a frequency sweep standing at that camera pose. Now, from this kind of training data, here's the objective we set up. And again, I said it's self-supervised, so there won't be manual labels, but we'll leverage the two streams together. And the key idea is to say, we want visual features that are able to predict whether echoes and the RGB view agree or don't. So that means during training, we'll come in with the RGB, we'll learn an encoder for it, we'll come in with the spectrograms for the binaural audio, and the binaural audio that's paired with this RGB photo will either be correct, meaning it's the one you would sample if you were looking at that picture, or it'll be wrong by some rotation offset. So it'll be the echoes you would have heard if you had turned to the right or behind you or the other way. Okay, so now because during training it's either right or wrong, then, and we're supplying this pair, we can train this multimodal model to predict, is it in agreement or is it not? And if it's not, you know, what's the offset? So that is a self-supervisable objective. And it's a good one, we think, because it's going to force us to find aspects of the visual stream that are predictive of the echoes we would hear. And to have that predictive power, it needs to be paying attention to the major surfaces, the main geometries, the big furniture in the space that's going to affect the echoes we get back. So that's the key idea. You're baking in the smarts of the given by the echoes, which give us a sense of spatial sound, into the visual encoder by making it have to predict one from the other. Now, once you've done that, I mentioned a moment ago, you know, we want to use this for visual tasks. So actually, in this case, we're supposing there is no more sound. I mean, you know, for the task we're going to tackle, but there will always be the RGB. And so what we are coming back with is an RGB encoder that can process the images alone. So now what we can do is use these pre-trained visual features, the encoder I just showed you from VisualEchoes, to pre-train for spatial tasks like depth estimation. So a monocular view depth estimation, you take one photo and you estimate the depth of the scene at every position. So the RGB at the top has the ground truth depths in the second row. If you train a state-of-the-art monocular depth estimator from scratch, then you get the third row estimates. And if you do that same model, but pre-train it with VisualEchoes, you get the bottom row. And I hope you can see a little bit how they're, you know, some cleaner depth estimates coming in the bottom versus the third row. Now, these images are from a standard depth estimation data set called NYU. And importantly, this test is actually a so-called sim to real challenge for us because we trained this whole thing with SoundSpaces, which is simulated from real scans, but simulated audio. And now we're testing it on real world photos that are in this data set from unrelated or, you know, disjoint environments. So this is cool because it's a hint that what we're learning in SoundSpaces can start to translate to real world data. And again, the message here is that the pre-training from sound helps a purely visual task. And in fact, we've measured this. We've also done the same kind of process for surface normals and for visual navigation, where we have to find something making sounds in the environment. And the message of these results to us was that, yes, it's better than training from scratch to have learned the acoustics, or to have leveraged the acoustics to learn a better visual encoder. And in fact, it's even competitive, sometimes better than what people do with very heavy manually labeled images for pre-training, like ImageNet pre-training. Okay. All right, so the very last bit of this talk, in the last minute or so, I'm going to come back full circle to this challenge of visually guided audio separation. So what I've just been showing you is how, you know, spatial sensing should, you know, is very rich in the sound, and we can leverage it for our vision tasks to do mapping, to do depth estimation, and so on. Now let's come back to source separation, but think of it in this embodied way. Embodied, I mean, you've got the ability to move in a 3D environment and hear spatial sound. So existing methods, including the ones I showed you at the beginning of the talk, are not active or embodied. They're passive because they process video. And the video is pre-recorded. We have no control over it. It's whatever it was, and we'll try to do a good job of separating it. But we're now starting to pay more attention to this challenge, and we'd like to take it into the active and embodied domain. And the idea is this: if we have a smart agent who knows how to move around a house, then it should move in a way that could help it better solve an audio separation task. And of course, as throughout the whole theme of this talk, we'll do this by not only looking and being smart about what we see, where to move, but also, of course, listening. So why would this be useful? How is an agent going to be smart to move to do audio source separation? So this cartoon tries to illustrate that. Suppose there's 3 sound sources in environment, S1, S2, S3. And suppose you have a robot who started at the star position. And its job is to listen to the mixed binaural sound from all those sources at once, but separate out one that's of interest, maybe the person who's speaking over by the counter here. Now, if it just stays put, it'll do the best it can with whatever it hears and sees. But if it, in this case, if it moved and traveled all over here to the side of the counter, then it may have a better audio view of this third source. And notice it doesn't mean like go and stand on top of the third source, which might be useful, but might be not. It's going to a position in this case where the sound from source 3 would be audible and closer to, but still blocking some of the effects of sound 2 and sound 1. So this is meant to convey kind of this interplay between what a 3D environment will do to sound and what we can see, what we can hear, and where we ought to put ourselves in order to be prepared to best hear the one thing at the cocktail party that we're trying to hear, say. So this is a new task to our knowledge, agents that navigate to do separation better. And we developed an approach called Move to Hear to handle it. What it does is have 2 main parts. One, a separating network that takes audio and learns to do the separation continually and with a sequence of observations over time, together with a reinforcement learning loop that keeps observing the sound, but also the images in order to choose actions. And here actions are movements in the space. And so this reinforcement learning loop is going to keep hearing things, seeing things, and then deciding where to move the camera and microphone next. And to make that do it well, to be smart about separation, we train it with a reward that gets higher, the better the separation becomes. So think of an agent that's just learning by reinforcement how to move depending what it sees and hears so that it gets better at performing the separation task. So we train this model, and I'll just leave you then with a final example of applying it, just to make the problem more clear. So we have multiple sound sources here, a speaker.
No, I don't. I've used playback in films before, and my mind has a tendency.
Second speaker.
Stop talker, and she goes off in all different directions, and it seems complete chaos. But the more you look at the part.
And then the third object, the third source here, the piano. Okay, so the agent hears all these, but hears them all at once.
No, I don't.
And she goes off in all different directions, and it seems complete chaos. But the more you look at the part.
Okay, so imagine your robot, walks in the front door, all these things are happening, but it needs to like start paying attention to one of those human speakers, and it knows which one it cares about. So in the middle, I'll show you how the agent learned to move to do that. And on the right, again, you see the agent's egocentric view. So the 3 sources are the red squares. The one it wants to hear better is the circled one in green. And so it actively moves around. And as it moves around, it's going to see different things and hear different things. And over the course of this episode, it decides to place itself down here at the bottom of the scene. So it reaches that target source, the one it's trying to hear better, but it actually moves past it and then stops here. And what can we read into the trajectory chosen by this reinforcement learning agent? It does seem to have gotten closer to the source it cares about, but it's kind of using parts of the environment to block other things. Like source 3 is going to be dampened by the fact that it's standing by a partial wall, and it's gotten pretty far away from source 2, so it'll be easier to separate it out. Okay, and then the result, here's what it predicts for the latent monaural audio associated with that source.
About the live singing was that it allowed for multi-camera shooting, which is my personal favorite way.
So it's starting to highlight that speaker's voice among all the other backgrounds. It should sound like this if it's perfect.
It allowed for multi-camera shooting, which is my personal favorite way to.
Cool. So this is some of our early results. We've also quantified how good these models are. Our model is compared to things you might do that would be non-active or paying attention to where the sound's coming from, or et cetera. And the results are pretty promising, but also plenty more work we'd like to do to make it more general and more accurate. All right, so this is the end of my talk. I've covered how sound provides us in vision with important cues for semantics and spatial understanding. And I've highlighted some of those results from the group lately in separation and in mapping and shape understanding, as well as this platform we introduced called SoundSpaces, that a lot of the experimentation for the spatial work is happening. Now at the bottom, I'm highlighting the student authors and first authors on all the work I shared today: Rohan, Shannon, Unat, Sento, Sagnik, and Ziad, who have done this amazing work that I get to represent today. And with that, I'm really glad to have your comments and questions.